Our universe is a place of immense wonder. It stretches far beyond what the human eye can see, encompassing billions of galaxies, each with its own unique set of stars, planets, and cosmic phenomena. The vastness of space is both humbling and awe-inspiring, reminding us of our small place in the grand scheme of things. It is full of mysteries. From the enigmatic dark matter that holds galaxies together to the elusive dark energy driving the universe's expansion, there are countless phenomena that challenge our understanding. These mysteries are not just scientific puzzles, they are profound questions about the nature of reality itself, mysteries that challenge our understanding. Black holes, for instance, are regions of space where gravity is so strong that nothing, not even light, can escape. They warp space and time in ways that defy our conventional understanding of physics. Studying them pushes the boundaries of our knowledge and forces us to rethink the laws of nature, mysteries that ignite our imaginations. The northern lights with their ethereal glow and meteor showers with their fleeting brilliance captivate our senses and inspire wonder. These natural phenomena remind us of the beauty and complexity of the universe, sparking curiosity and a desire to explore further. Today we will explore three such mysteries. They are quantum entanglement, time travel, and the simulation hypothesis. Quantum entanglement, a phenomenon where particles become interconnected and instantaneously affect each other regardless of distance, challenges our understanding of space and time. Time travel, a concept popularized by science fiction, raises questions about the nature of time and causality. The simulation hypothesis, the idea that our reality might be a sophisticated computer simulation, forces us to reconsider the very nature of existence. Each of these topics has profound implications. Quantum entanglement could revolutionize communication and computing, leading to advances we can scarcely imagine. Time travel, if possible, would have far-reaching consequences for our understanding of history and the future. The simulation hypothesis, while speculative, challenges our perception of reality and our place within it. They force us to question our place in the cosmos. Are we merely observers in a vast, indifferent universe, or do we play a more significant role? These questions have fascinated philosophers and scientists for centuries, driving the quest for knowledge and understanding. These concepts may seem like science fiction, yet they are grounded in scientific theory and rigorous philosophical inquiry. The line between science fiction and science fact is often blurred, as today's speculative ideas can become tomorrow's scientific breakthroughs, but they are rooted in scientific theory and philosophical inquiry. The study of quantum mechanics, for example, has led to technologies like MRI machines and quantum computers. Philosophical questions about the nature of reality have inspired scientific investigations that push the boundaries of what we know. Join me as we journey into these fascinating realms. Together, we will delve into the mysteries of quantum entanglement, explore the possibilities of time travel, and ponder the implications of the simulation hypothesis. Each step of this journey will bring us closer to understanding the universe and our place within it. Prepare to have your mind blown. The universe is full of wonders waiting to be discovered, and the journey to uncover them is as thrilling as the mysteries themselves. Imagine two particles light years apart. They are connected. When you measure the state of one particle, something amazing happens. The other particle's state instantly changes to match. This is quantum entanglement. It's strange, it's real. Albert Einstein called it spooky action at a distance. He was skeptical, but experiments have proven entanglement to be true. It's a fundamental aspect of quantum mechanics. It challenges our intuitions about space and time. The implications of quantum entanglement are far-reaching. Imagine computers that are exponentially faster. This is the promise of quantum computing. Entanglement is the key. Quantum cryptography offers unbreakable encryption. Entanglement ensures secure communication. It's like having a secret code that's impossible to crack. And then there's teleportation. Not of people, yet, but of information. Entanglement could revolutionize how we transmit data. The future is entangled. Time travel. It's the stuff of dreams and science fiction, but is it possible? The answer lies in the nature of time itself. We experience time as linear, always moving forward. But Einstein's theory of relativity paints a different picture. Time, according to Einstein, is relative. It can be affected by gravity and speed. This means time travel is not just a fantasy, it's a scientific possibility. Section 5. The fabric of time, relativity, and time dilation. Imagine a clock near a black hole. Its time slows down compared to a clock on Earth. This is time dilation, a consequence of relativity. It's real. We've observed it. Astronauts on the International Space Station experience time slightly slower than us on Earth. It's not noticeable to them, but it's measurable. They are time travelers, moving slightly into the future. Section 6. Backward time. Travel. Paradoxes and possibilities. Time travel has always fascinated humanity, sparking countless stories, theories, and debates. The idea of moving through time, whether forward or backward, opens up a realm of possibilities and paradoxes that challenge our understanding of reality. Forward time travel is possible. We experience it every day as we move from one moment to the next. In fact, according to Einstein's theory of relativity, traveling forward in time faster than usual is theoretically possible if one were to travel at speeds close to the speed of light or experience strong gravitational fields. But what about going back in time? This concept is far more complex and riddled with paradoxes. The idea of reversing the flow of time raises questions that challenge the very fabric of our understanding of the universe. This is where things get tricky. Paradoxes abound. One of the most famous is the grandfather paradox, which questions what would happen if you traveled back in time and prevented your grandfather from meeting your grandmother. If you succeeded, you would never have been born, and thus could not have traveled back in time in the first place. Imagine traveling back in time to prevent your own birth. This creates a loop of contradictions that seem impossible to resolve. If you were never born, how could you exist to travel back in time to prevent your birth? If you succeed, how could you exist to travel back in time? This paradox highlights the potential impossibility of changing past events without creating inconsistencies in the timeline. These paradoxes suggest limitations to backward time travel. They imply that certain events in the past may be fixed and unchangeable, or that any attempt to alter the past would result in a self-correcting timeline that prevents paradoxes from occurring. But they don't rule it out entirely. Some theories propose that alternate timelines or parallel universes could exist, where changes to the past create a new, separate timeline rather than altering the original one. Wormholes, theoretical tunnels through space-time, offer a potential avenue. These hypothetical structures could connect different points in time and space, allowing for the possibility of backward time travel without the paradoxes associated with altering the past. They might connect different points in time, but they remain theoretical. Despite the intriguing possibilities, wormholes have not been observed, and their existence remains speculative. The mystery of backward time travel endures. As our understanding of physics and the universe continues to evolve, so too will our exploration of these fascinating concepts. The possibilities are as endless as the questions they raise. Section 7. The simulation hypothesis. Are we living in a computer program? What if our reality isn't real? What if it's a simulation? The simulation hypothesis proposes just that. It suggests we are living in a sophisticated computer program created by a more advanced intelligence. Think of it like a giant video game. The world seems real to the characters inside, but it's just data. Could our universe be the same? Section 8. Evidence and implications of a simulated universe. There's no definitive proof we're in a simulation, but there are hints. Some scientists and philosophers argue that the universe's complexity and the fine-tuning of physical laws suggest an underlying design. This idea isn't new. It has roots in ancient philosophical debates about the nature of reality. The simulation hypothesis posits that our reality could be an artificial construct created by an advanced civilization or even by our future selves. The laws of physics seem oddly fine-tuned for life. Constants like the speed of light, gravitational force, and the strength of electromagnetic interactions are precisely what they need to be for life to exist. If any of these constants were even slightly different, the universe as we know it wouldn't be able to support life. This fine-tuning has led some to speculate that it might be evidence of a designer or a programmer. It's as if the universe was designed. The intricate balance of natural laws and the emergence of consciousness are phenomena that some argue are too perfect to be mere coincidences. This perspective raises the question, if the universe is a simulation, who designed it and why? Are we part of an experiment, a game, or a form of entertainment for some higher intelligence? And the pixelated nature of reality at the quantum level is suggestive. Quantum mechanics reveals that particles exist in a state of probability until observed, much like pixels on a screen that only render when needed. This has led some to draw parallels between quantum behavior and the way computer simulations operate, where resources are allocated dynamically to render only what is necessary. If we are in a simulation, what does it mean? Who are the simulators? What is their purpose? These questions are profound. They challenge our understanding of existence and our place in the universe. Are we simply characters in a grand narrative, or do we have the agency to influence our reality? The implications of this hypothesis touch on ethics, free will, and the nature of consciousness itself. They challenge our understanding of existence. The simulation hypothesis forces us to reconsider what we know about reality. It opens up possibilities that are both exciting and unsettling. Whether or not we are in a simulation, exploring this idea pushes the boundaries of science, philosophy, and our imagination, encouraging us to seek deeper truths about the universe and our place within it. Section 9. The interconnected nature of reality. Quantum entanglement, time travel, and the simulation hypothesis are not isolated ideas. They are interconnected. They point to a deeper reality, one that is stranger and more wondrous than we can imagine. These concepts challenge us to expand our thinking, to embrace the unknown. They remind us that the universe is full of mysteries, waiting to be unraveled. The journey of discovery is just beginning,